Okay, seems like we're live now.
Okay.
Yeah, okay, that looks good. Okay, so I guess let me introduce our speaker. Welcome everyone to another Safari live seminar today. Today we have Professor Gennady Pekhimenko, who's an assistant professor at the University of Toronto in the computer science and EC departments. And also he's a faculty member at the Vector Institute in Toronto. And he's a SciFar AI chair. So he's working a lot on machine learning and artificial intelligence these days. But Gennady is no stranger. He actually gave a seminar a few months ago on his broader research agenda and research topics. And it was quite interesting. So we decided to deep dive into some of the research that his group has been following. His group is called Ecosystem Efficient Computing Systems Group at the University of Toronto. And they've been looking at architectures, algorithms, tools, and benchmarking for machine learning in general, and systems for machine learning in general. And today, Gennady will talk about machine learning tools in action. Gennady has been at Toronto, is it 4 years now?
I started my 5th year this fall. Right?
Oh, 5th year, okay. Oh, almost 5 years, let's say. Yeah, time flies. It's been a while. He graduated from Carnegie Mellon University from Safari. Basically, he's a Safari graduate, one of the earliest Safari graduates, let's say. And then he went to Microsoft Research, spent some time over there as a researcher. And then he moved to University of Toronto. Mm-hmm. And he essentially works in the intersection of machine learning systems and architecture, so doing exciting work. So we're looking forward to hearing about machine learning tools that his group has been developing in the past several years. And Gennady, with that, please take over. And anybody is welcome to ask questions on YouTube or Zoom, please.
Thanks a lot for the introduction, and thanks for the chance to talk for the second time. So the tools is something we're really excited to build and push for the to the community. Unfortunately, when you typically give talks, there's not enough time, so you can just briefly mention some of that and you focus on some other specific items. But luckily, I had a second chance to talk and Safari Research Seminar, so I can actually go and talk deeper about the tools that we built. As Arnold just said, please, at any point of time, if you have a question, feel free to interrupt me, right, and ask questions. So I'm happy to take them live. Okay, so just remind you for the people who, might forgot some part of my previous talk, there is this dependency circle if you want to optimize machine learning workloads, right? And we talk about benchmarking last time. We briefly mentioned performance metrics, and we spent a lot of time here talking about how we can address different bottlenecks, essentially different research papers published at the top conferences, ranging from algorithms in conferences like MLSys all the way to the hardware, so like papers at Iskar Micro. So today, though, I'm going to talk about something slightly different. I'm going to talk a lot about the tools. Last time, I just briefly mentioned that we had portfolio tools. I'll start where I essentially had to stop last time. So I just, again, show you how the classical profiling tools look like. So this is a memory profiler that run on a BERT-based model, right, that reports you where the memory goes. This is a tool that could tell you, for essentially averaging across the run, what is the maximum memory consumption of the model and where the, all that memory goes. It's an important tool to have. This is a classical tools we get used in the CPU world, where you just, take the binary, run it, and get the profiler results, and then some external tool or internal tool would plot it. This is helpful, but this is not the best you can do. So what I want to show you is a new generation of tools we built that are both interactive and try to do a little bit more than just reporting things to you, that these tools actually try to make predictions for you. So last time I briefly talked about this tool, Skyline. I'll just remind you again, this tool is really an outlier paper for me. It actually was published in the Human-Computer Interaction Conference called UIST. And it's important because it shows how powerful the tool can be if you actually put extra effort into that. So Skyline is essentially interactive in-editor performance visualization tool and debugging tool for DNN training. It was motivated by the fact that people were not happy that the models are both slow and consumes a lot of memory. And there were a lot of posts by people complaining about those tools. And Skyline essentially has several features. It has key performance metric reported to you as you would do using text tools, but it does this in interactive fashion. So you can, click on different parts of the model on different layers and it would tell you what's going on right now. It's live in the sense that as you change the model, things will change, right? And it's connected well so that it can even change part of your code directly. So the metrics we report is the classical metric like throughput, both predicted and the one that you actually achieve, and memory consumption, that's what you care about. So it's like, what is the maximum memory you have versus how much you actually consume right now. We can break down the time and the footprint per layer. Remember, most of the models have a nice structure, so you can actually see and attribute different parts for it, and you can look at how much per layer is consumed. You can also might be interesting to have different looks, like you can want to see forward versus backward pass or activations versus waits. All of that is available in the information for each layer. We have a way to connect things between this nice plugin built on top of PyTorch Atom Editor, and to the level that I'll just zoom in the next video, right, that you can actually see and adjust things. So it's like one really cool feature that we have is you see, so if you want to improve the throughput, we allow the people to really just, raise the bar here, and the batch size that allows you to get higher throughput can be automatically adjusted to reflect the speed you want. Okay, so this is a very nice front-end tool that we built. This is right now used to connect with a lot of other different intelligent tools that we have in the group. And this is all open source. We keep supporting it. It was originally built on top of Atom. Right now it's supported tools. Should definitely try it out. It's very powerful. Okay, so this is more or less the brief repetition where I stopped last time talking about the tools. And the same student, Jeffrey, recently published a tool called Habitat, which was actually developed before Skyline, but it happens that it was only published recently in USENIX ATC conference. And this tool is a predictor that tried to predict the computational performance for deep neural network training. So let us have a look. What is the problem that we try to address in this work? So essentially, there are many GPUs available right now for deep neural training. So that even the commodity ones from just one vendor, NVIDIA, already can go more than 10 of them different ones. Each have a different cost and performance trade-off. And it's not easy, especially for less experienced machine learning developers, to decide which one is good for them. So the observation we make in this work is that the DNN training is highly repetitive, and it is possible, even though the workload is very time-consuming and can take days or weeks to train a model, the performance of a single iteration is predictive or can be used as a predictor of the total runtime performance, because performance-wise, most of the iterations are more or less identical. So this motivates us to create a tool that would help people predict execution time on different GPUs using two techniques. One is called wave scaling, which I'm going to define in this talk, and another one is just using pre-trained MLP, multi-layer perceptrons. And we built these two ideas into a new tool called Habitat, which is again open source and supports PyTorch. And we're going to showcase several studies on how Habitat can be helpful for people to make a decision on making the right choice of the GPU that is helpful for them. Again, everyone knows that deep neural training is important. There are a lot of use cases across different domains: image classification, machine translation, speech recognition. And what makes them all very common is that there is a huge computational overhead to train those models. Because of that, people try to build a lot of different hardware. So there is essentially a Cambrian explosion in hardware for training, and it's very difficult to make a choice. So Habitat is making, poses this big question, which accelerators you would want to use. In this work, I'm going to focus about which GPU we want to use, but in general, our group will look in on how you make prediction across different accelerators. So why is that a problem? Well, the thing, essentially, you had this paradox of choice. There are so many GPUs available. There is something available in your workstation, something available potentially in your local cloud, in your university or your institute, like the Vector Institute you have. And there are GPUs also available in the clouds, like AWS or Google Cloud or Azure, right? And the question obviously you ask is, what's the performance for my model, right, and my framework? What would be the cost for me to train the model using all these things? And one thing we found in this work, there is no one-size-fits-all choice here. The correct answer really depends on what the user needs, the user demands, and the user model, right? And this is why it's become challenging for people. Of course, when you pose the question like that, people usually say, oh, there are a lot of different solutions to this problem. And typically reviewers tell us, why you not do something else instead of what you do? So we wrote actually a separate section in our paper saying, why not just, and we summarize everything that people were coming up for a while. So the first obvious choice, people said, why don't you measure directly? So why do you need to make predictor on a different GPU? Like, isn't that easy to go and access it? And there are several problems with that approach. First of all, you need to pay for the access to the GPUs, and it's not cheap. If you want to use state-of-the-art, NVIDIA GPUs, you actually need to rent the whole node, right, with multiple GPUs. It's quite expensive. It's also tedious to repeat that access and setting up all of those, many models that you might have, and you might not have an expertise to do that, and you might not benefit from that. So why spending the money and not getting anything, right? Another, suggestion people says, can you just use the benchmarking results? There's all those different benchmarking suite. There's the one I talk about, like MLPerf, right? And there's the benchmark suite we built, TBD suite. There's one from Stanford called DonBench. Can you just use those ones? And the answer there is also not very convenient because it only had a handful of models. Chances are your models are not there and might be not reflective of the performance of your model. And results are not available for all GPUs. It's only available for a handful that NVIDIA decide to report, right? And obviously there is another question is why not using some simple heuristics by, for example, just guessing the performance by just using the flop ratio of different GPUs. And here I'm showing you the graph that you can see that if you're going to use these heuristics, they not always work. So if you're just going to use flops as your metric, you would see that actually using T4 as a reference and then trying to predicting the performance of other GPUs would lead to a huge error in runtime prediction, as high as like 60% sometimes. So simple heuristic can lead to high errors, more than 40% for all these different GPUs. So yes, you can try them out, and none of these simple ideas would work. So you need actually something smarter than that to make it practical. But we make several key observations in this work. Again, deep learning users may already have an existing GPUs, right? So most of them developed a model on their machine, so they already have a GPU available. And DNN training is a repetitive process with short training iteration, short as in the order of like hundreds of milliseconds. So we can use existing GPUs to make an iteration of the execution. And then we can use that iteration to make a prediction for other GPUs. So you make a measurement, for example, for your own desktop 20i GPUs, right? And then understanding both your model, execution graph, and their differences between different hardwares, we can actually make an intelligent prediction what the runtime would be on these different GPUs without actually having physical access to them. So this is what this work is doing. Any questions so far? So this is the motivation for the new piece, Habitat. Do we have any questions so far?
We don't have any questions till now.
Yeah, that's fine. We can just continue.
Yeah,
okay,
sure.
so this is essentially the motivation right now. I'm going to actually tell you what we built to solve the problem. And essentially what we do, we build Habitat, a runtime-based performance predictor. The first step of Habitat is profiling all operation in a training iteration on an existing GPU. So we had a model code, we take the GPU that provide us and we perform profiling. And then for prediction, we use two different techniques. And I'll explain later why we have to use two different techniques. One is called wave scaling and another one is Nlp. So it's essentially, there are unfortunately a lot of different kernels and some can be predicted by one way and can be predicted by another way, and they are significantly different. So I'll talk about that. Then using those two predictors, we actually do performance prediction on the iteration execution time. And from that, we can get the training throughput, and we can also make an estimate on how much cost it would be for you to train on this different GPU, and you can make your decision afterwards. Again, as I mentioned before, it's an open source Python library that supports PyTorch 1.40, and we're planning to keep supporting future versions as well. So please play with it if you're interested. So let's go into some technical details right now. How does Habitat actually works? So just a very quick background for some people that might not know too much about GPUs, right? Just a very quick background reminder. So GPU kernels are there essentially the entities that the programmer provides us. The work is divided into thread blocks that essentially have the same code but different data, right? For example, we have a GPU kernel with 8 thread blocks. Then those thread blocks are running on the actual GPU, consist of on multiple ASMs, streaming multiprocessor. Each of these can run a finite number of blocks concurrently. So blocks run in round-robin fashion, scheduled onto the ASMs. And GPU kernels actually execute in waves of thread blocks. So you run one wave and then you run the second wave, okay? So this is the way at a very high level how the GPU works, which should be enough for you to understand the ideas behind wave scaling. So this wave operation gives the name of the main technique we used here called wave scaling, right? So essentially, the idea is that given a kernel execution time on one GPU, for example, on a GPU A, we have a kernel that runs for 200 microseconds, right? Wave scaling predicts the kernel execution on a different GPU, say GPU B, that have a different number of ASM, have different architecture, right, and other features as well. And it does this using the both GPU's hardware specification. So let's go through the example to get the intuition on how that works, okay? So this is what we're trying to get, moving our kernel from GPU A to GPU B, what the runtime would be right now, okay? So in the line with its name, wave scaling works with thread block waves. So first, it computes how long a wave takes by dividing the kernel execution time by the number of the waves. So computing the number of waves for GPU is relatively straightforward. It can be used using some of the profiling tool that CUDA provides, and that's what we did. Then, to predict a wave's execution on GPU B, we need to understand what are their different bottlenecks that we might be affected. So essentially, wave scaling scales this 100 microseconds using 3 major factors that we believe are the main sources of their effect on performance for the machine learning workload. One important factor is the memory bandwidth ratio between the two GPUs. So depending on how more bandwidth you have, your kernel can run faster, your wave can run faster. The number of thread blocks in a wave, in other words, the wave size matters, obviously. And another obviously important metric is the clock frequency, the speed of the GPU itself. So let's go over the intuition to see why each of these factors works. Again, remember, this is intuitive examples. in in the paper, we had a very detailed formula and explanation on how to do the wave scaling prediction. So here I'm just trying to get you some intuition. So imagine you have GPU A with 2 SM, GPU B with 4 SMs and the same bandwidth at the beginning, right? So now suppose that GPU B would have twice larger bandwidth, assuming, right? Assuming that that kernel is memory bandwidth bound, that essentially would shrink the runtime of the wave by half. So you would get 50 microseconds. If in contrast the bandwidth is lower, then the wave execution times will double. And that's essentially how you make the prediction with respect to the memory bandwidth. So this is why that factor matters. Of course, it's not always so simplified, but this is the way that factor affects the runtime. Okay. Next, wave scaling also need to take into account the size of the wave. Again, suppose the kernel is memory bound, bandwidth bound for now. So if you can have a GPU where you can only run twice, where your wave size is twice smaller, then essentially the runtime would increase, right? And in this case, it essentially would be the same, right? So you had more SMs, right? But you can only run one on per SM, because remember, you can have more SMs, but the SM's architecture might be different between different GPUs, okay? So essentially, this is how the wave size affects things. Finally, the kernel is not always memory bound. I will actually get back to that when I talk about the results. Most of the machine learning kernel are typically either memory bound or compute bound. And there is a few that are super compute bound, and there are a few and there are a lot of different smaller ones that are memory bandwidth bound, and both important for performance. So if you get a compute bound kernel, then the main decision factor is actually the frequency at which different GPUs would run, right? And then essentially the performance would be affected proportional to the clock rate between the different GPUs, okay? Okay, any questions so far?
No.
Okay.
Not
so
yet.
Just, to complete the example, suppose the kernel is memory bandwidth bound and the GPU B's memory bandwidth is 2 times higher, right, than the memory bandwidth of GPU A. That would shrink the runtime, but then we also need to keep in mind the GPU B's wave. If it happens twice as large because it has more SMs, we notice then in this case, right, I would need to take this into account. So we would get essentially the same runtime potentially, despite memory bandwidth and the SMs and the number of SMs being different between different architectures. So all these 3 factors plays a role, and we have, as I said, equations that was well, motivated intuitively, but also had the math behind it on how to make this prediction. Ideally, so essentially we would then make prediction afterwards. So ideally, that would be it. Unfortunately, life is more complicated. So the one important wrinkle that a lot of vendors that build machine learning libraries, they don't generous to you, they don't preserve the code between different iterations of GPUs. So for some very important, usually compute-intensive kernel, they vary the kernel execution and run completely different algorithms between different versions of the GPUs, different generations of the GPU. That you cannot handle with wave scaling, because you cannot make conclusions about the runtime from one hardware when the code is completely different. So essentially, wave scaling assumes the same kernel, right, and when it works, but the DNN operation that had architecture-specific implementations, we call them kernel varying. Those are a handful, but very important one: convolutions, linear dense layers, LSTMs. For those, we build a special predictors using MLP technique that trained on many different small inputs for those layers, and it can make then prediction for them on that hardware, again, without the access to the hardware from the user perspective. So this is pretty much the key main ideas behind Habitat. I will now go and show you the evaluation of it. And hopefully you would see why both techniques are needed and that you would see that the correct decisions are actually helpful in practice. So we're going to look again at the accuracy. We're going to look at making correct decisions. Those are real use case studies we built at Vector Institute. For evaluation, we use 6 GPUs spanning 3 generations from P4000, P100 of Pascal, then Volta, and then Turing architectures. We use 5 models. We use image classification ResNet inception. We use LSTM model GNMT. We use transformer-based model transformer. And we use adversarial network DC-GAN. So we try to really cover the whole spectrum of popular machine learning supervised models. And it's all built on top of PyTorch 1.4. So the first question you obviously ask is how accurate is Habitat making a prediction? Does it really worth it? So essentially, the main metric here is running a model on this GPU using this batch size. What would be the runtime on a different GPU? And say we might predict 96 milliseconds, the actual was 94 milliseconds. That metric that we would care here is the error, which would be 1.9% error in this case. Okay. So again, the paper goes into all details on all different pairwise, errors across different models, and we try, trying on different GPUs and predicting all different other GPUs we have. On average, what you're going to see that Habitat makes accurate prediction with an average error of around 11%. You can ask whether that's good enough. I will show you soon it's indeed good enough. It will look at 30 different GPU pairs multiplied by 5 models across 3 different batches. So there's a cross product of a huge space. So ultimately, the error itself doesn't matter that much. What matters whether the people can make the correct decisions using this predictor. Is the error affect their choice or not? So here's one scenario that we actually have at Vector Institute. You had a GPU in the cloud that you might need to rent and pay for it. So say you want to train a GNMT model, a popular machine translation model, based on LSTM, and you have access of P4000, and you want to decide which cloud GPU you want to use. And then say a couple of years ago when we make most of the measurements, there were V100, T4, and P100, the main ones available in the cloud. So what essentially the measured and predicted would show you that we can actually carefully predict what the runtime would be in most cases. And then, depending on what you want, you can either pick V100, so that would predict you to have the best performance. It indeed has the highest performance. Actually had slightly better performance than we predicted. But if you not only care about performance, raw performance, but you care about performance per dollar, then actually T4 GPU would be a better choice because you know the price of it. So we also correctly predict that T4 would be the best choice in terms of performance per dollar. So why won't you use something like best GPU all the time? Well, let me show you one example when you would see that it actually using the best GPU is not always the best choice. So for example, you want to train DC-GAN and you have access to 2080 Ti GPU, is a popular gaming GPU that a lot of desktop has. And the alternative is to use V100 that back until recently was the best GPU available in the cloud. And what you're going to see is that Habitat can correctly predict that the V100 for that model, despite being a much more expensive GPU, only marginally improved the model performance, just around 10%. So if you had your own GPU only 10% below, would you really invest money and time into running in the cloud? The answer is probably not. And the thing is, we actually correctly predict that. So the fact and the intuition that sometimes companies want you to do to buy the most expensive hardware is not always the best case. Okay, and the key thing we can predict that that's the case, and this is model specific. Okay, just to summarize, there's way more details and results in the paper. We had prediction breakdowns, we had sensitivity study for our NLP model, We do predictions onto additional GPUs and so on. We had discussion about extensibility. So there's, I guess, one thing I didn't show here, but that's important probably to cover, is why we have both techniques at the same time. So the problem is that the kernel varying one, they only done for a few kernels, but those kernels are important. So they would cover around 50 to 60% of the execution runtime. On the other end, the tail of the other kernels you execute, there are hundreds of thousands of these kernels. So it's impractical to build NLP models for all of them. That would be, you know, very difficult, right? And they keep changing all the time. So essentially, you have two classes of the kernels, one that vary a lot, very time consuming, but there's only a handful of them, and everything else that are really small, but cumulatively still 40 to 50% of the runtime execution. And for them, wave scaling works well because the algorithm doesn't change, right? Nobody would bother rewriting the code specialized for those kernels. Okay, in summary, I want to say that we make some interesting observation in this work that GNN computation has special repetitive pattern that enabled new analysis opportunities. We use runtime-based information to make iterative execution time predictions. Habitat leads to the correct decisions in the case studies that people actually care in real scenarios. And the hardware landscape is growing and users need to help choosing effectively. We keep developing Habitat. We are now working on integrating TPU and Trainium. Trainium is a new Amazon chip predictors that would allow you not only predict between GPUs, but also between different accelerators. And we also right now working on integrating Skyline with Habitat. And essentially the way we envision it, there would be a special tab where you can show the throughput predictions across different GPUs. For example, if you had 2070 GPU, you can use it as a reference point, and this is the runtime prediction on other GPUs for your model. Okay, this concludes this part of the talk. Any questions? So this concludes Skyline and Habitat. Any questions so far?
I guess I have two questions.
Sure.
So first of all, thanks for the presentation. So the first question that I was planning to ask is that, so across the training iterations that you're talking, right? So did you see any difference in runtime based on some like computation-based optimization, let's say sparse optimization? So what I'm suggesting is that, so as the training goes, more values are going to, let's say, 0 or near 0. So the computation is like getting rid of those computations at all, right? So did it show that the performance is varying across iterations of training, or does
Very
it?
good question. Yeah. So there are two parts to it. First of all, whether that happens, and then they can, solve that problem if it happens. First of all, for until recent GPUs, 800, there was no even hardware support for sparsity. So essentially people discussed that in research papers. There was no chip that actually benefit from that. So we did a sensitivity study, and back then input didn't matter. All zeros versus all random has very little effect on performance execution. That's not going to be like that forever, but that's true as of now. So then this is what is true. So it's essentially, there's no difference. We sample iterations at different periods of time for different checkpoints. There was no, like a runtime difference is really minor. Like what would make a difference is DVFS changes of the GPU, right? If it decides to go to a low frequency mode. If not that, there's no difference. But moving forward, I think Google didn't announce it, but I'm pretty sure they published papers on sparsity. Something in the future TPU v5, v6 will have sparsity support as well. And the question, what we're going to do when that happens? Well, what helps there is sparsity doesn't change dramatically either over a quick period of time. So we actually, I actually work on sparsity with Amazon, and we did measurements. So the sparsity tends to be stable over time, over long periods of time. So essentially, and hardware is not going to support, as of at the beginning, at least, random sparsity. So it's all going to be like 4 to 2, 2 to 1. So essentially, if you had high level of sparsity, you can guess that that kernel might get a 2x boost from sparsity, but it's not going to get a random boost from sparsity. So essentially the kernel that had sparsity right now, an 800, there's only one option. You either get 2x speed up or you don't get any speed up, right? So that's literally it. So it's very coarse-grained sparsity support. Why is that? Because fine-grained sparsity is a very difficult problem. Hardware doesn't like fine-grained flexibility. It needs a more coarse-grained structure to amortize the cost. Yeah. So I think even when sparsity appears, that it still would be a way to handle it.
So that means the sparsity itself is also predictable. So we can take that into account and predict accurately.
And even if you forget about hardware, like I did this experiment before a couple of years ago at MSR, and we look at sparsity, if changes very little over time per layer. So you can make it very predictable, right? So you can know per layer how it's going to behave. It would be extra work, but it can be handled. So it doesn't go up and down. It's usually very, similar over time. Yeah.
Thanks. Yeah, that answers the question. So the second question is that, did you also expect, let's say, the similar performance projections in cloud GPUs where it might have, let's say, multi-tenant support? So if it is shared across different users, then that might change the performance projections.
Very good question. In fact, I actually try to work and push multi-tenancy on both GPUs and in the cloud. The short answer is there's no multi-tenancy right now, and you don't expect real multi-tenancy right now, and there's no predicted in the near future from the cloud perspective. Why is that? Yes, there is a new feature called MIG, right? That you probably heard, right, in Ampere, that allow you to slice the GPU. I actually talked to AWS cloud people, and from their perspective, this is not cloud safe. So essentially, what that means is nobody would allow you to run a piece of the instance on the same GPU at the same time. The main problem is there's no crash isolation. Like if the driver crashes, everything crashes and they cannot easily isolate the side effects of memory and all the throw hammer things. So it's very unsafe, right? As of now. So NVIDIA provides the feature. The only way to benefit that feature is if you buy the GPU yourself, and then you slice the instances in your own framework. Then you might need to handle that, right? But then you already own the hardware. You already run it, probably buy it on a regular basis. So you need that predictor way less. You have the whole access to hardware. So the people who are going to randomly run quick runs, they're not going to go into sharing mode, right?
Oh, understand.
Yeah. So it's still a long path for real multi-tenancy support. We probably need a few more generations of GPUs, and NVIDIA goes into that route. Right now, it's not really sharing. Right now, it's really hard partitioning. That's what MIT does.
Okay. Yeah. Thanks. Yeah, I think that's it from my end. Yeah.
I have one question also, Gennady. I think this is quite interesting. It's certainly an important problem. It reminds me of performance prediction works when it's actually more general, right? You could potentially generalize it. That was going to be my second question. But before you get to that, how do you take into account tensor cores, for example, or accelerators inside the GPU, let's say, the way I like to think of them?
Great question. So the theme that I'm going to talk next, we can handle things like that.
Okay.
So,
okay, sure.
So essentially, this is not just tensor core, but in general, any other optimization of the software, hardware, and it's a problem, right? People publish hundreds of papers on ML every day. So how you can handle that? So there is a way to handle tensor cores on top of it. And Habitat actually discussed it. And this paper, Daydream, was published a year before, even though it was done in parallel. So actually, Habitat describes how to use Daydream into its own decision to handle these hardware features.
Okay.
Actually, not that difficult. Yeah.
Yeah, I figured, but I guess I'll wait for your description of Daydream.
Yes.
The other question is like how generally applicable it is. Certainly GPUs have their own characteristics, but potentially you could apply it to other machine learning accelerators as well, right? That work on, let's say, SIMD exploitation.
Yeah, so if you look at, if generality is a very interesting direction, obviously. So if you just stay within domain of machine learning and look at different accelerators, my initial thought, initial results suggest it's actually easier to do it for TPU and other systolic array architectures than for GPUs. GPUs has a lot of leftovers from graphics that makes things complicated, while those systolic arrays architectures, they actually, single-threaded in order, 5 finds. It's like a huge matrix multiplication where there are no surprises, right? You put a kernel on it and zeros, no zeros, doesn't matter. It's going to execute as much as it's supposed to execute. It's not very flexible. So actually predicting systolic array runtime, and that's the main execution part, is actually quite straightforward and very accurate. So the main challenges with TPUs and Trainium is not predicting when they run on systolic array, it's predicting everything else. When they don't run on systolic array and they run on some crappy implementation of CMD units that they have, or they had context switches and all those things that are not documented, that's hard. But the systolic array architecture is very difficult, easy to predict. Then there is other things like graph core and Cerebrus architecture that's very different. They're not in the cloud really yet, right? They had some customers, but those are very, unique customers. So we don't have access to hardware yet. I have access to graph core and Azure cloud, but again, I'm not even sure they're big enough to spend time on them. They had distinct architecture as well, obviously. They might need to look more carefully. But it doesn't, it seems like mainstream stuff is still doing systolic arrays. Like it's AWS Trainium and Inference chip, obviously TPU, Intel Habana chips, they're all systolic array based. So whether the Cerebrus approach would become dominated or not is something, it's very expensive. That's what I learned, right?
Sure.
So you can show cool demos with it, but then you do performance per dollar. It's like, I'm not convinced yet. Right?
Sure, yeah. Yeah, it's certainly an interesting approach. And
if you look generality beyond machine learning or look at other domains, the key feature that will make it possible is repetitiveness, right? The whole reason it's like, why can I do it for a general CPU workload? Because it has tons of phases. It might be completely different from phase to phase and change over time. Here you execute for a week, but every 200 milliseconds are almost identical.
But for example, for repetitive scientific applications, this could also work, right?
Yeah, that's a great, that's something we put in the discussion, yes. So essentially high performance computing workload with the repetitiveness, same thing, same observation would work.
Okay.
The same thing.
Okay, cool. One last question. I think you already kind of answered it because it leads to different, let's say, applications perhaps, but I assume it's very difficult to predict across different ISAs, right? If you take, let's say, an AMD GPU versus and try to predict the performance on an NVIDIA GPU, you need to do some extra things.
Yeah, we didn't do this yet, and the main reason is all the ISA challenges is I tried to work with AMD, and their software stack was not ready, unfortunately. So we cannot get the baseline performance counters and everything, right? So we'll get back to that exercise when it's more mature, right? I think one good thing is that frameworks like PyTorch has a good abstraction level where that little things like ISA differences doesn't matter that much. So I need to know how fast you can run matrix multiplication, right? Or batch norm and all those things. And if I know that, I don't really care what you're doing with your ISA, right? Because at the end of the day, all of you are going to run the same executional graph, and that's your API. And then there's a tensor primitive, and that's how well you run this tensor with a certain op. That's what matters for me. So we can luckily abstract out most of the complexity of the hardware, which is good, right? We can actually, separate these layers, right?
Yeah, yeah, that makes sense. I think if at the high level of the computation description, you can tie it to the performance without really relying on the ISA at all in the prediction, that makes sense.
The harder thing right now, to be honest, is the fact that the ML hardware vendors like NVIDIA, especially, they pick the path of specializing manually for each architecture and changing algorithms. So essentially, you don't see the code if it's closed source, but based on its behavior, it's clearly a huge spaghetti code with a lot of if statements that runs different algorithms, 10 different versions of matrix multiplication depending on dimensions. And it's closed source, it's hard. The new stacks that people built in MXNet and Amazon and I think Microsoft, it's all open source. So that's much easier to deal with,
Sure.
right? Right, yeah. So I really hope that would be what people would go for. AMD is trying to build their own stack, also open source, but I really don't see the users yet. Like, there's not a lot of users of it, right, other than AMD. So.
Yeah, maybe over time.
Their hardware proved to be very good. So we benchmarked AMD chips a couple of years ago, and their matrix multiplication was as good as NVIDIA's one, but the software stack back then was very immature. I think we got another question here. When you transfer from one platform to another, are the same features important throughout the platforms? What would happen in case you train at a platform which doesn't have a specific feature like Tensor Core and predict to another platform like the Tensor Cores? It's a very good question. Features matters, but again, luckily things can be abstract out. So if you think about Tensor Core, this is only affecting matrix multiplication, right? So in a way, this is the same as kernel variant feature for me that would run either on regular CMD units versus running on Tensor Core. And I'll show you in Daydream, this is something that can be handled relatively easily because Tensor Core performance is actually very predictable. It gives you a scaling factor of 2 or 3 depending on the use case, but that's pretty much it, right? So, and it only affects a very handful of kernels. So everything else is not affected. There can be other unique features of the hardware, but I guess you need to see that right now the hardware that's available, most of the things can be abstract out. Okay, again, the honest answer would be only when we do it end to end and report the results, we can claim, yes, everything can go smoothly over it. But we already had some, limited success with TPU and Trainium, so I'm cautiously optimistic it's doable.
I wanted to ask you a question related to the framework. So
yes, sure.
As far as I understood, like the framework for you actually doesn't play a kind of a varying role, no? When you are doing your extrapolations.
You're absolutely correct. It's just the engineering overhead. So we pick PyTorch. That's a dominant platform right now for Vector Institute. It's about 88% of all the workloads. Like if you count GPU hours are running PyTorch, right? So we pick the one that mostly used. But yes, everything that MXNet, TensorFlow, something that has a computational graph can work with that.
But do you expect these like frameworks to maybe be more adaptive to the target platform and therefore change the kernel generation based on what type of platform do they have as target?
Very good question. I mean, the way I understand the people, like we actually collaborate with PyTorch people, the people who develop it, like in Facebook, like they had a dedicated team for, and they try to be hardware agnostic and all the features agnostic as much as possible because they want not to lose anyone, right? So essentially, most of that, they try to keep everything optimization-wise to the lower level of the backend so that nothing in the framework itself is overly specialized. In a way, like if you look at, say, TPU versus GPU, right? Ultimately, from machine learning perspective, what differs if where you had one accelerator, another accelerator, you had matrix multiplication, you send it back over some interconnect and then send it back, right? What happens on the hardware doesn't really matter as much because the whole CPU to GPU or CPU to TPU, high-level architecture is the same, right? Yes, the bandwidth changes, the compute capability changes, but nothing else really changes from the framework perspective. So no, frameworks try to be as general as possible, so not to pick favorites.
Because like I was thinking that if you may have a GPU with more memory, maybe like new fusion opportunities, they may arise that you may want to take advantage of. And then you are no longer in the ops execution, but you may want to fuse between different ops and create new kind of like kernels on the fly, more like XLA kind of approach.
Yeah, so fusion and all of that is definitely an option. But remember, when we do predictions, we work on the execution graph. So we see, so essentially there is ML compiler within PyTorch or the XLA for TPUs, and both, do fusions and we see the fusion decisions, right? So when we do predictions, we're already aware of the fusion decision. If essentially some kernels, two kernels fuse, and have a different implementation, we would essentially, to make correct predictions, we need to make sure we profile that as well, right? So that the baseline would have it. So we would need to enforce it. But you're right that that would add some extra challenge, but luckily it's all visible to us. If that happens, we would need to treat it as a different piece of code, essentially, right? So because it's a different kernel right now.
Yeah,
It's really the kernel change, right? We would need to treat it as the change in the kernel itself, like a kernel varying operation.
Yeah, thank you.
So it would complicate things, but it won't make it like, you know, a dead end. Okay, thank you. Any other questions?
I guess that's it for now.
Okay.
If I get some questions, I'll ping you. Yeah.
Let's talk about Daydream. So Daydream is something we published recently in collaboration with Microsoft Research USENIX ATC last year. And the idea is to accurately estimate the efficacy of optimizations for DNN training. So essentially, the goal of this work was that trying to predict the effect of a transformation that I read on an archive article, and there are hundreds of those, without actually fully implementing it, because that can take engineering weeks or months of time, right? So the Daydream essentially try to avoid that engineering overhead and try to effectively, you know, making predictions, looking at dependency graph analysis. So we try to track. So why the prediction is difficult is because there are a lot of parallel kernels, sometimes thousands of kernels running in parallel, and it's hard to understand the dependency in what works when, right? So that's what Daydream solves. It has a systematic way to abstract the GPU kernel execution using dependency graph analysis. It can done kernel to layer mapping efficiently, and it come up with an intermediate simple language that describe the transformation rules, such as tensor cores and mixed precision that were mentioned before, to model a diverse set of optimizations. And elevation will show that that we can have prediction with a very high accuracy across many different models. So again, why this work was motivated? The work was motivated by seeing all, you know, fellow machine learning developers and researchers struggling to keep up with an exponential growth of the, you know, papers published, right? So it's even more aggressive than the compute. If you look at how many papers published in ML community, it's like really growing. It's like closer to 200, I believe, right now. So following this up is difficult, and even if you're interested in one or two, periodically, still you need to implement that. The problem is the quantity is there, quality is not necessarily there. So a lot of these papers are implemented in weird benchmarks on random frameworks, and you want to know how it's going to affect your workloads. So it's very hard for ML programmer to identify the efficacy of new algorithms. And they have all these different questions like, why is my DNN training workload running slow? And what is the bottleneck? All of that obviously leads to which optimization X would improve my performance if I had problems. And what if I get the latest GPU and my computer is 2x faster, what the speed would be, right? So you see there is some relation to habitat as well, but the main focus here is, you know, how I'm gonna scale across large number of GPUs, how I'm gonna try all these different optimizations and do it in one nice coherent way. Like all these questions about what if I upgrade to a faster networking, how much speed up I get for my models, all these questions that people want to ask. Essentially, dependence analysis that used in this work is not completely a new concept. People use it in many other different non-ML contexts before successfully in systems community. It's quite efficient in ML case as well, because there are computational graphs for many models that had a very nice, you know, graphical representation that's relatively easy to manipulate with, but it also leads to some challenges. So essentially the goal is, given training implementation X and optimization Y, what would be the effect on the runtime of y applied to x. So like what would change after the optimization is applied. We essentially have training implementation, right? And then we had a Daydream profiler that's unfortunately was done with MSR and still proprietary, so we can fully open source Daydream. And that has some very good profiling capabilities that standard PyTorch tool doesn't have. It can have the information for traces and kernels. And one of the challenges is how to map things to each other. So Daydream was able to attribute one to each other. Because the problem is from the user perspective, you run layers. That's what you define in your PyTorch implementation. This is layers of your network. But the hardware run kernels. And those kernels are not easily matchable to layers, right? They're just always different things that you don't know, like had random names. So somehow you need to associate it. We were able to do it with a careful profiling and timing characteristic. We were able to associate kernels to the layers. And then what we do when there's an optimization Y coming, we actually go and apply this transformation optimization on that graph itself, on the dependency graph. And because we know how the graph runs, what's parallel, what's sequential, we can actually make manipulation with the graph that would represent the optimization itself. And that can be done without fully implementing optimization end-to-end, just manipulating the graph, right? And then we can simulate the runtime with actually running it, taking into account all the dependencies, all these gaps in the runtime. This is what makes it complicated, right? So the challenge number one is that there are thousands of tasks and dependency needs to be tracked across CPU threads, GPU streams, and interconnects. The second challenge in the some optimizations operate on the kernel level granularity, others operate at the layer level granularity. So how you can make that happen. And the third one is ability to easily model the Rose DNN optimization, because there are huge difference in what different DNN optimizations can do. So the tracking dependencies is there's a lot of careful engineering that needs to be done that the student did, right? Hongyu found that GPU kernels are highly serialized for most DNN training workloads, right? That allows you to build nice graphs on the CPU and GPU timeline on what execute when and what synchronized with what. And we cover all these different, dependencies, CPU to CPU, and GPU to GPU, CPU to GPU launching, right? All of that is taken into account when looking at the runtime. The challenge number two is trace layer correlation. So optimizations might operate at kernel level, yet still requiring the knowledge of DNN topology. So remember, I think David mentioned the fusion and all these things. So you need to have visibility of this type of transformation, right? Low-level traces have no domain knowledge, and naive approach at synchronization everywhere shows very poor performance and overhead. That's such that prediction won't make sense. So essentially, what we were able to do, right? We were able to that's what happens if you add synchronizations here and there to, align things nicely. So those, what we were able to do, we were able to collect the real-time profile timestamps with very low overhead. And then we can, knowing that the dependency information in the graph, we can track what's running after what carefully with very little overhead to instrument the framework. So we don't add any extra, instrumentation, because the problem was when we add all the synchronization to understand what is what, the performance would be non-reflective of the real workload anymore. And there's no alternation of the dependency graph, so it's synchronization free. And the third challenge, again, I'm going over that briefly, you can read way more, through the papers, is there a huge set of different papers published in the space. They have different optimization goals, such as improving hardware utilization or lowering communication overhead. And they use tons of different strategies, and there are multiple papers published on each of it. The claim we try to make in this work that despite all these differences, they all can be, characterized by using a very simple intermediate language that describes what this transformation does for the computational graph. So essentially in this paper, things highlighted in green that was implemented end-to-end, meaning we implemented it fully and also implement our predictor, and they're highlighted in italics and bold. Those optimizations will show how to do, but without end-to-end implementation. So essentially the transformation rules, what we found is that there are just a few simple primitives that describe majority of this transformation. That's one of the key observations of this work. So there is a selection operator that returns tasks of interest for future process. So remember, we talk about mixed precision and tensor cores. Remember, when we talk about tensor cores, they cannot run with FP32, right? They actually run with FP16 or TF32 right now, but with lower precision types. It means to be efficient, you need to use them with mixed precision. And that means mixed precision is only applicable to certain types of kernel that can actually run well. And for them to be selected, you need to apply a select operator. So only certain kernels would be affected by tensor cores or mixed precision. So for example, here you write select task is on GPU, right? Then you can run things select type is convolution. All of that would select the right kernels for you. That's one primitive. Another one is where you add kernels, right? Or you delete kernels. So essentially a lot of transformations really either fuse kernels or do fission and fusion. So most of the transformations you can think of from the graph perspective is just manipulation with the nodes. And then there is also scheduling. So that's essentially these four primitives. We were able to cover tens of different research papers and research approaches. And here, this is the very favorite one because everyone asked about tensor cores and about mixed precision. So really, the tensor cores, instead of fully, like if you look at the tensor core support in PyTorch, that was like months and months of work and a lot of engineering effort, right, to get it supported. But to just simulate its behavior, this is just less than 10 lines of code here. And as you can see here, right, you just literally the code itself is just, we were able to micro benchmark tensor cores. And essentially, if you use mixed precision and you're using tensor cores, certain kernels, the ones that starts with Volta or wgrad or SGEM, right? Those are the kernels that do matrix multiplication and convolution operation. That speed up by about 3x. This is the net effect, right? And people reverse engineer that behavior, and it's stable over time for large dimension. And if you would just use FP16, but without tensor cores, things would speed up just roughly by 2x because NVIDIA implemented FP32 compute units using FP16 ones. So if you switch to FP16, you get twice more multiplications and additions. So you get about 2x speed up. So this is essentially what you do. You do kernel filtering, select, and then scaling factor, right? So the kernels themselves don't even change here. They just scale in runtime. Obviously, scaling by 3 or 2 doesn't mean that the whole runtime scaled by 2 or 3. They might overlap with something much longer and that would have zero effect. Or they might be on the critical path and they had a huge effect. So this is what the dependency graph allows us to solve. Any questions so far? So this shows you how simple those annotations, descriptions of the transformation can be, because you don't need to know all the low-level details on how the tensor core is implemented. You only need to know what it does for your kernels. And that's what you need to describe. And that can be very easily profiled. In fact, NVIDIA usually reports that in their micro benchmarks.
We don't have any questions till now.
Okay. So so like we get in the paper about, like in huge appendix, 10 optimization examples, each of them around 20 lines of code, right? So a lot of, like we try to show that it's not just one technique is easily describable. A lot of different techniques can be easily described this way. And then we'll just go over, evaluation against similar GPUs, frameworks and everything. And so we are gonna, the baseline here is the iteration time of running Y without X. That's the baseline. And then ground truth is when we go and actually put all the engineering effort and implemented optimization Y on top of X. And then there is a prediction. That's what Daydream did without implementation, just using the description of why on what it does for you. And we always look at all these different, popular models. So the first question, of course, is how accurately things can be predicted. So here we're looking at several different techniques like Nlp and Fuse Adam and others. So you can see that a mixed precision had a huge effect on bird-based runtime, and the ground truth and the prediction were only 5% apart, right? And that error is varies. Sometimes it's a little bit more, sometimes a little bit less, but on average it's less than 15%. And then we implement Fuse Adam as well, and you see the error is not high. So in general, you see that the error, that the key metric that would hopefully help us to make right decision on the runtime is making a careful prediction. Why do you need prediction? Because that would tell you what that idea would mean for your framework and your model, and then you would know it's worth implementing. You know that a lot of papers doesn't have proper implementations, or you would see that they don't make sense in your context. It would really saves you a lot of engineering time, and it helps both researchers and developers. Yeah. So the average error is about 8%, 15% maximum on what we show here. We also show that the same thing can be done not only on a single, like remember for Habitat, we focus on a single GPU, but here we're able to do distributed training as well. For BirdLight, we show that you can, on all these different, networking bandwidths and different configurations of GPUs per machine, we can also make, very accurate prediction, and the error is typically below 10%, right? And then we did distributed training across all different models. So you can look at all the detailed results. The key takeaway here, it does accurately predict performance for multiple TNN models, which allows you to make careful predictions. And here we show an effect on the priority-based parameter propagation paper, MLSys 2019. And that what we found that this technique works well for some models, not for others. For example, here you see for ResNet 50, it was not working as great. So baseline and ground truth, you see, are not too far from each other. It's slightly better, but not too bad. And you see the prediction is very close to it as well. So it would tell you that if your model of interest is ResNet 50, this is not worth implementing. But if your areas of interest is VGG19, we would correctly predict that is indeed good. So this is an example show that we can very carefully find the subtle difference between some techniques work on a certain model, but on a different model, right? And we can carefully predict that. Okay, so to conclude here is that to our knowledge, Daydream was the first system that aims at estimating efficacy optimization for DNN training without actually fully implementing them. It used dependency graph analysis, similar to Habitat. It's sync-free, so some people try to do synchronization before, but we found that it's completely altered execution. So the runtime you get afterwards is irrelevant because they don't match the reality. And we come up with an intermediate language that can be helpful to describing a lot of, different optimizations using just simple graph transformation rules. And Daydream is able to accurately estimate the efficacy of optimizations across a wide range of DNN optimizations. Okay, this is all on Daydream. Any questions?
So I have one question from Gagan. So he asked, it seems that Daydream works while training a model, but it's not always possible to train a model from scratch, like BirdLarge or any of the language mask modeling, right? So then the question is that can we use a pre-trained model and optimize some aspects of the model? Let's say prune a part of it, or let's say some optimization based on the data flow, right? And then use Daydream on top of it.
So I don't fully understand the questions. Like so here we assume that the model is given, right? So that someone implemented the model, right?
Mm-hmm. Yeah.
And
so
then,
I guess the question he's asking is that can we take a pre-trained model and optimize and apply Daydream's optimization estimation on the pre-trained model to predict the performance improvement of the fine-tuning phase.
Okay, so I guess for people who don't understand is the way NLP works these days, right? So BERT-like models, transformer-based model, have two stages. One is called pre-training, one is called fine-tuning. From the systems perspective, there is no difference. Remember, this is not ML optimization. This is a systems paper, right? It just predicts the runtime. So in that sense, first of all, really, if you the fine-tuning and pre-training doesn't have to be similar, but in fact for BERT they're quite similar. There's only one layer that's different, right? But the thing here is that, yes, say you had a pre-trained model, right? Then that's already was given to you. Then you're running a fine-tuned model. What fine-tuned model, it's usually a relatively quick run because the models are mostly trained. If you want to speed up the fine-tuning still, it's not that usually not that slow, right? Compared to pre-training, fine-tuning is usually fast. If you want to speed up fine-tuning itself, right? What I would do, I would take a fine-tuning model, right? And try to apply optimizations to it, right? So from the system perspective, this is two different workloads, pre-training and fine-tuning, right? If somehow you want to use the information from pre-training into fine-tuning, it might be possible, mostly because the models are almost identical. But I don't see the need for that, right? Because it might be actually quite different, right? In general. Right now, it's not. They only add the last layer to be different, right? So essentially, from this perspective, this is a system level optimization predictor that tried to say whether optimization Y would speed up, say, fine-tuning, right? And then you will need to take fine-tuning model, right? Take its dependency graph and do the prediction, right? Doing a prediction on fine-tuning using pre-training, I would say, is not required, and it's not that difficult because running a few mini batches and collecting, like, you don't need to make any runs here at all. You just build a dependency graph, you just compile it, right? So there is no need to, and like run some profiling. Whether the profiling on BERT pre-training versus fine-tuning, it's an interesting question. I think they use different batch sizes. Pre-training is usually trained like a large scale, very large batch, right? So I think things won't be reusable directly. So topology is very similar, but the batch size and other things might be quite different.
I see. Yeah, perfect. Then I think that answers the question. I don't have any questions till now. Maybe if someone has a question, then we can chime in. Or
David?
we can move on.
I think David muted himself.
Sure. So just a clarification. So I understood that you were actually like running at least to get a baseline to use as your time like diagram that you would just then manipulate.
Yeah, you need to have a profiling run for the baseline. You're correct.
Okay. So then my question is like, I would like to get more insights on like, because I really like this kind of partitioning that you have done. So like you are saying with almost no implement or like with a partial implementation, no? I think that here is the key. So you still need to implement somehow the transformation in order to create a model, no? That you are going to use later for the estimation of what is the impact of these local optimizations in the overall execution, right?
Yeah, essentially the whole, so essentially when you give a model, right, using a high-level interface like PyTorch, then what you're going to get at the end is an execution graph, and that's where we do the changes. So what we're trying to do is taking what would happen within that dependence graph, go and manipulate it and run it through a simulator, right, of our own, that the simulator, knowing the runtimes of all the individual kernels before and the dependency, that's the tricky part, we can figure out what the net effect of these changes would be on the total runtime.
But like my question then is like, how easy it's like, because when you were showing like this kind of like a mixed precision, no, that someone else was profiling to like the factor 3, factor 2, but if you have to do that yourself, so what is the amount of effort?
Yeah, so I see, that's a good point. Yeah, so that's where the part that I guess we can't automate yet, because this is, well, for mixed precision, it's very easy. Like those results are provided by NVIDIA. So what you can do is someone publishes a paper and says, we were able to do blind blur, and then that say, this kernel speed up by that much or that much. You would need to make some assumptions, right? You either profile it yourself, right, a little bit, or you trust their numbers from the paper, right? There's no miracle there. So you will need to take some input on what gets faster, right? You either profile it yourself, right? But the thing is, it's very much easier to do than the full-blown model change, because it's much easier to micro-benchmark an individual kernel, right, than showing the net effect of the whole, for the whole model, right?
Yeah, this I can see. Yeah, thank you. And then like a question.
Absolutely correct. There is still complexity and intelligence that has to be done, and I don't think it can be done automatically. It has to be done by humans.
Yeah, I see that. So then like related a question.
It's difficult. Like imagine you would need to write something that would describe an archive paper automatically into this intermediate language. It's difficult.
Yes, that would be cool. So I have a question like related to the simulator that you say that you use to extrapolate, no, like the benefits. So there, I understand it is like a kind of you're recreating the runtime environment almost, no? And you are just...
No, that's just in the profiling helps. The profiling already tells you all the kernel's detailed characteristics. What you only do, you remove the kernels and shift the kernel. Like you had all the dependencies and they're quite sequential, going up and down a little bit. Like look in the paper, you will see it. Okay. Some examples. And then what you do, you remove some boxes, insert some boxes and making some larger or smaller. Or that's everything you do. The tricky part is very non-linearly shifts the whole timeline. So you cannot do this manually, right? But the tool can do it very accurately. You don't need to create any environment, right? You just kind of alternate the boxes and then you just change the graph and then just run it end to end in a simulator saying what the runtime would be now after the change. You just go through the graph of the dependencies. That's it. You don't need to create a real environment for execution. You just, for each box, you had start and end.
Okay, I'll check the details in the paper. Thank you.
Yeah, it's actually easy. Like the trick is to get the dependency correctly and make sure don't miss anything. The parallelism is tricky, right? Because CPU and GPU kernels has a lot of overlap here and there, so you need to properly model that. Like for example, with mixed precision, what's tricky for some models it helps, for others it doesn't, because sometimes those kernels are not bottlenecks, so you speed up them by 3x, but they overlap with by another CPU kernel that's much slower, like memcopy, and then it doesn't benefit from mixed precision. In other cases, a huge benefit because you're bottleneck by matrix multiplication, and we can cache that well. But it's not only that, we can capture all this, like we implemented one paper on batch normal, optimizing batch norm. And that thing was taking a batch norm, slicing it into two kernels and fusing it with the previous and the next layer. And this fusion and fission we were able to model very accurately as well. But you're right, there is some overhead to profile how fast it will be. Okay, so if there are no more questions, I still had another piece to talk briefly. That's ArrowScope, which is a cross-stack profiling for reinforcement learning. And this is a joint work between my group and the group of Vijay Janaparedi at Harvard. And we're going to definitely switch gears. This is something recently was published at MLSys 2021. And that's going to be quite different from the previous work because reinforcement learning workload are very different in nature and have a very different bottlenecks. They do have, a huge value right now. So not just playing games, which is nice. But recently people show that you can beat humans at game of Go. You can model robotic locomotion. People actually, the most impressive I think use case was done by Berkeley and Google, where they show you can train robots, manipulation with objects using reinforcement learning. All of that is quite interesting. One challenge with reinforcement learning is that training time of those models limits progress. And this is non-supervised learning. So a lot of things you learn about the previous pieces is not true here anymore. You're actually not bottleneck by accelerating most time. So yes, it takes a lot of time to train. For example, AlphaGo 0 was taking 40 days to train. You need to try many different RL algorithms in parallel. Now, training time is limiting. Another problem that reinforcement learning workloads are not the same as your supervised learning workloads. And the difference here is someone gave you the labeled data set that's done by humans. Here, there are no labeled data sets. So you need to run simulator of some sort that models the environment or the game that gives you the output as you go. And essentially all the tools that, for example, NVIDIA designed, and even we ourselves designed, was done for GPU-bound workloads. We actually found that those tools going to give completely wrong information for reinforcement learning. They might tell you that you're fully bottlenecked by the accelerator, like 99%, when in reality you're below 1% sitting on the accelerator. So those tools can be very misleading. So, and the main fundamental thing here is the CPU time matters a lot, because most of the time, RL workloads will be on the CPU. But why is that? Why that happens? We also show that profiling overhead need to be handled properly. You can get, if not done properly, the way that people are doing it right now, you can get 2x almost runtime inflation. Well, the first question is why we don't use existing technique, and the answer is they have different workload structure. So what's the difference? So if you remember anything from this talk, the solution doesn't matter as much. The key problems, that's what's important. So the supervised learning algorithms, if you look at C++ backend and Python frontend, what's happening, you had initialize the computational graph, right? That's happening in the Python part. And then you go into C++ backend, right? That would be running backpropagation algorithms on the accelerator, typically on the GPU. The problem in reinforcement learning, and we'll take an example, Atari Pong game trained with DQN, is that there is a simulator that's running on C++, but then the state has to go to the Python level. Then that states would have to generate an inference stage to see what the prediction would be. That's an inference. And then that inference would have to give you feedback back to the Python level to update the result on the next experiment running on the simulator. And then that simulator going to go back and run on the C++ backend, right? And so on, right? And essentially you then cached some experience. As you can see, fundamentally, there is really a lot of transitions going back and forth between CPU and GPU and C++ and Python, and that transition has a very negative effect on the overall performance and utilization of the hardware. So this is how the overall data flow of the reinforcement learning algorithm would work, and not specifically GQN, any of them. So ultimately, the difference leads to three major problems. So training data, right? So in one case, the training data is nicely resides in the GPU memory where you just copy and you just run back propagation and you just keep reading through it. Here, the training data doesn't exist. You need to keep run a simulator, copy it back to the Python level, manipulate with it, and run experiments with it. The second big problem is training loop. So here, because of you had a lot of data you can run in parallel, that's all labeled, you run data parallelism approach, and you can run very large models that amortize the cost of training. You can run very large models on accelerator. The problem here is your training loop, right, resides, significantly here, and the model you have, right, is actually quite tiny. So if you look at here you run a really large model, here run a tiny model, because you don't have large enough inputs at any point of time. So overall, these three problems make reinforcement learning profile look very different. In fact, there is an anecdote that we observed then back in the day when people work on supervised learning, they always try to get the best GPUs for their training. Now, we found that the people who try for reinforcement learning, they actually try to get the CPU with the highest frequency, usually the one that doesn't have a lot of GPUs, but has the best CPU, which is very non-intuitive for the whole community. You always want to get the most number of GPUs. And the reason for that is because they're frequently CPU bounded. Okay, so where does the NRL workload actually spend time? I gave you it at a high level, but if you go really deep into the problem, where that the problem is there and where's anything we can, do it. So what we found from the beginning, if you want to profile those workloads, you need to build a cross-stack profiler, because a lot of time you spend, you go between CPU and GPU back and forth, and it's fundamental. You can easily get rid of that. So essentially that stack has algorithm, it has deep learning backend, CUDA API and simulator, and there are GPU kernels. And you see those are running at different levels. So there is something running on the Python, there is some part that running on C++ backend, but running on the CPU, and there are GPU kernels that doing inference and backpropagation and running on the GPU, right? So there is all these layers of complexity that add up here. And essentially, as an algorithm, this is, without looking into details, this is your algorithm. We just describe you here a key parts of it. There is an inference. This is where you are given an input and the label, you're getting a prediction. Then there is a simulation where you get, a new data point, right? And then there is a backpropagation. That's the thing that, given the results, it's try to update the parameters of the model to do better prediction, and then you do inference again. So there is algorithmically, this is the three big stages you always have there: inference, simulation, and backpropagation, right? Inference and backpropagations are running on accelerator typically, right? Although sometimes they use CPU as well, because inference is so inefficient on a GPU, it might be just faster on CPU. And simulation is usually running on a CPU. Then essentially the cross-stack scoping allow you to understand what is happening where at different periods of time. And this is what RL-Scope can provide you. So essentially the idea behind RL-Scope is to do cross-stack scoping, cross-stack view of the CPU, GPU time spent, and it works with different frameworks like TensorFlow, PyTorch, and different simulators, and we're extending its support right now. And another important thing that we face as a big challenge is we need to correct for profiling overhead. Everything here is so fine-grained that profiling overhead of regular GPU and NVIDIA tools is humongous. It can bring to completely wrong conclusions. And you need to be able to get rid of that overhead and compensate for it when you do profiling. Otherwise, you make wrong conclusions. And the key contribution here, we're building an open source tool that can profile very efficiently RL workloads and can give you minimum and meaningful feedback on how things can be improved. We did a very extensive RL workload survey working with our ML friends, and we show how CPU GPU time varies across different algorithms, simulates, and how conclusions can change on what needs acceleration. So from the user perspective, the only thing you need to do is so-called annotation. Remember, I told you that there is the simulation, inference, and backpropagation part, but it's very hard to just looking at a random code define what is what. So what we really need from the user is to tell us what is simulation in their code, what is inference, and what is backprop. And all RL algorithm we've seen has the stages. So the only thing we need for you to annotate that, because automatically it's very hard to solve. Then, if you give us this annotation, we would know how to attribute different parts of your runtime to either simulation or inference, right? And then RL-Scope, we can do the rest of its magic. It would transparently intercept all the kernels using NVIDIA Captai tool, right? And it can see which runtime goes to CPU, which would be, this color, and GPU, which would be this color. And then we can also have the annotation on what's running on Python versus what's running on CUDA, this is what's running on the backend, right? And that, no recompilation is needed. It supports TensorFlow and PyTorch, and it's easy to use. So how do we use it in some real workload? Oh, yes, and there is a overhead calibration. I'm just showing you here that when you enable profiling, one thing we faced is because the kernels are so tiny that profiling overhead is humongous. And you need to calibrate for that. So we were able to come up with the way to identify how much overhead we typically get on different things, and we can scale the whole execution of different parts properly so that we account for the overhead. That was actually a very challenging task engineering-wise, because we were getting wrong conclusions otherwise. Okay, and we also do a cross-stack event overlap, right? So we can essentially, if you go in at the timeline, we can see, we can show you where you are with respect to, being in Python versus CUDA. We also can tell you where you are at this point, whether you're on CPU versus GPU, right? So you can see, how things change over time, right? So you can see how the stack bar builds up, and then you can make an analysis on which part of your code needs to be optimized. Okay, so in the interest of time, let's just go quickly look at some of the results and characterizations we did. So there's one important thing we evaluate was different versions of PyTorch and TensorFlow and some features that they have. So let's look at this first study. So essentially, for people who use machine learning for a while, you're probably familiar with the, eager execution, right? So, that essentially, as you execute things, right, and go through the graph, things executed immediately, right? And this is the typical, approach that PyTorch uses, right? There is another approach that TensorFlow used for a while, right? Where essentially you build the graph first and then you execute afterwards. This is a graph model. And so essentially one is easier to deal and debug, which is PyTorch, that is so popular among ML people. And the graph model originally was faster and more optimized. Things change these days. And TensorFlow also implements so-called outer graph model. That is a hybrid approach between the two that gives you a good functionality for debugging, but also a good way to get high performance. So for a while, you can read anecdotes online, people arguing what is fast and by how much. For RL workload, it was not clear what's true, what's not. And that's the right answer here is to have the tool and do the measurements yourself. So we did that and did a systematic study here on a RL algorithm called TD3 and DTPG. And as you can see here, here is a PyTorch eager execution, right? And here's TensorFlow outer graph, TensorFlow eager execution, right? And you can see where the time really goes. So you would see, first of all, that neither outer graph nor graph outperforms the other and within 19% of each other. So even people who are claiming the outer graph might be, not very efficient, they're actually very close to each other. Then the second observation is that the eager execution is giving you a speed up of 1.9 to 4.8 in contrast to the outer graph and graph execution. So what does this tell us? It means that graph execution mode was actually less efficient on the TensorFlow because there's a huge benefit in TensorFlow going from here to here, and it's less so in PyTorch. It means that PyTorch eager execution is actually done much better than the TensorFlow one. And this is the way to, argue for that. But we not only see this, we can see why this happens, right? So we not just tell you the anecdote that one is faster than another, we can see what's happening. And the reason is, if you look at the timeline, you're going to see that here we got 5x reduction in Python runtime. So it went from here to just here, right? So outer graph reduces the Python time to just 7% from 59% in graph for inference and backpropagation. This is the reason why it's efficient. So, and we attribute it to a specific change, right, it makes rather than guessing. And you can, look and analyze more things here. And you can conclude that Errol scope can, easily attribute the good performance of outer graph to a source, to the real source, which is it reduces the number of Python to backend transitions. Those are the ones, remember, that are so painful in the reinforcement learning case. And this is what the outer graph can do really well. Okay. And finally, we can, we can not only tell you the runtime, we can actually explain why PyTorch can do certain things better than TensorFlow. So PyTorch eager is 2x faster than TensorFlow eager. And this is because not about anything else that people speculate on the web, but actually because of this Python to backend transitions done way more efficiently. Okay. And you can also find that there is not more than 14% of time is spent executing GPU kernels across all ML backends and execution models, and that the rest is entirely CPU bound, right? And that explains you why the performance of CPU is so important. CUDA API runtime dominates the GPU kernel execution, taking an average of 3.6x longer than the GPU execution itself. So essentially, Errol Scope is able to not only report the performance differences, but it can attribute it and correlate with things like transitions between different parts of the stack. And that's why it's quite important. And again, in the paper, we did analysis on a lot of other things. I don't have time to talk about it too much. This is some of the key takeaways that you want to remember. Well, this is one of the important things. At least 38% of training time is spent on simulation. So optimizing simulators is really important for those workloads because they spend a lot of time there. And like accelerators are not a big deal. So reinforcement workload right now is a nightmare for NVIDIA or Google because there is not a lot that happens on the accelerator. Almost all the overhead actually happens on the simulation part. Yeah, that's pretty much it. Any questions on Errol Scope? I intentionally make it shorter so we can finish in reasonable time. There are way more studies and details in the paper where we deal with the more complex Errol workloads, like dealing with Gore or dealing with real-time drones. Yeah. David, questions? Or
yeah, I think we have a couple of questions. So Konstantinos might want to go first. Konstantinos, can talk.
Yeah, thanks for the talk. I have two questions. One is related to DeepRL mostly, and the other one is more general and more towards microarchitecture. The first one is the following. So we have several emerging workloads like from completely different domains nowadays. So we have chess. Chess is a pretty emerging workload, like many million players play, and there are state-of-the-art engines who are ML-based or non-ML-based. The ML-based is coming from DeepMind, which is the AlphaZero one, and the other one is a history-based. It's a more complex workload that there's no clear way to accelerate it, or how do you map it into a GPU or an accelerator, or how do you, whether a company will go out and spend money to produce an accelerator just for this workload. And same thing happens, for example, with protein folding. Again, DeepMind came up with the algorithms AlphaFold. There are some classical algorithms who also have the same problem. They're more complex. There's no end-to-end way to accelerate them. There's nothing like that. So my question is the following. So does it make sense for these type of problems where DeepRL is one solution that can be promising now and is promising in the future, to come up with a general alpha-based or like DeepRL-based accelerator framework, let's say, or design, so that we can move away from algorithms like this, like the classical algorithms of protein folding or the state-of-the-art engines of chess, so that we can increase the acceleratability, actually, how much we can accelerate these algorithms and move away completely from classical algorithms and convert everything to DeepRL or these type of problems that we have a better idea of how to accelerate.
Yeah. Well, first of all, it's a complicated question, but I'll try to do my best. So essentially, my vision is that it's not like people didn't want to do acceleration before, right? It just, the reason why we had all these ML accelerators right now, because there is our killer workloads, like the ones that do make a difference, right? And if you're very pragmatic and honest look at it, there's not too many, but they're big enough. So we had something related to vision, right? there is object detection, self-driving, everything related to that. That makes it a big breakthrough, like something we envisioned to do only 20 years from now is now possible. And another thing is NLP workloads, right? So everything related to machine translation, speech, and all of that. It's a very big categories, but those are where the breakthrough happened and computers needed, and the market, it was so huge that it was a no-brainer to do hardware. I actually once asked Google when I was giving a talk there, why would you do a Tpu chip? Well, the performance, if you look at MLPerf results, is not dramatically different from GPU. And the honest answer was, it's not about fanciness, it's all about money, it's all about cost. So the GPUs are so costly, so it's actually not that, it's not a huge overhead to build the hardware of your own, because they had so many workloads internally at Google that needs training that would easily outweigh the cost of developing the chip. So why I brought up this example? So it all boils down to the market, right? So right now people build accelerators when there is a necessity, when there is a big enough domain that has a value and it's actually possible to do it. People don't always build ASICs. Sometimes people just prototype on FPGA when the performance are not as critical. But the minute you're confident on what you need to build, you will go and build the ASIC design. Then the question is how we can guess what of these emerging workloads is worth accelerating versus not, and how to make it generic. A lot of people are looking at it. I don't think there's an easy answer. I honestly think that, say, reinforcement learning is extremely bad workload for NVIDIA or Google. Like if you look at their numbers compared to CPU, it's not a huge difference, right? It's like, I mean, simulation time is what you're doing. So now NVIDIA is trying to make a simulator running on a GPU itself. This is definitely not a scalable approach. Can we make, like, let's take RL as an example. Can we even generalize RL alone? Not talking about everything. And that's already very challenging. I discuss it with my student for a year now. The problem is simulation can be anything. Simulation is essentially any random, so it's like accelerating any random CPU code, right? It's the same problem. Like, can you do it efficiently? Well, it's hard, right? It's a hard problem. So ML is nice as a deep learning part of it. It's nice because matrix multiplication is easy, right? Compared to everything else. But a lot of other ML workloads not necessarily would have the same characteristic. Again, NVIDIA tried to build libraries for everything that's useful, but it's a speculation at this point, right? If you ask me whether RL really have a industry use case, my answer would be half of the use case right now. Compared to deep learning that has 2-3 real use cases, they barely have any real use cases. All this playing Go and playing chess, it's more like a nice, mind games people like to play. But if you look at the real thing that would bring you money, the only thing they do right now is that the work I mentioned from Berkeley, that they do robot manipulation learning with RL, right? They had that's a group that published, like, I forgot the, I think they published 10 NeurIPS papers on that every year. So this is a very visible group. And this is the only real use case of RL that I've seen that had an industry potential, right? There is hundreds of other ML stuff around that probably not gonna click. And I don't think as an architects or system people, we should just jump on everything, right? We should wait and make it stable and make it converge, right? So, and then there would be things that does have a value. There are definitely things that will keep coming. So in my honest opinion, I'm not an ML expert, but deep learning is not an answer to everything. There will be new things coming in the future years, right? Whether it would be a RL or not a RL thing, I don't know, but something that is unsupervised is required. We definitely don't learn everything in a supervised fashion. Moreover, even if for supervised learning, when I teach my kids, I don't need to show them billions of cats for them to learn what the cat is, right? So they can do this way faster. You show them just once or twice. It means that the way we learn right now is very excessive, right? We waste a lot of power and compute for very basic concepts. Like one fundamental thing that's completely missing right now, we live in the world, in the environment, and our models learn without the environment, right? So they tend to, we try to learn languages right now without knowing what the world is. So there are fundamental things we can't translate properly because we don't understand what's feasible in the real world, what's not, right? And this is all part of our language. So all these interesting problems are there. How they're going to be described? They might be ended up being something like linear algebra, how people did things before, or something else, I don't know, right? So if you think there is anything generic we can build right now, I don't feel like it. Even for RL alone, it can be literally any CPU code right now. So people just take certain classes of simulators and try to accelerate that. Something I say is like high performance computing or physics simulators. But any general simulators you want to build for RL, it's hard, right? You need to build it from scratch. This is right now, it's more like a proof of concept, like Google demonstrated that AlphaGo can be done. And they did use RL because there was no other way. Like honestly, like if you look at their RL paper for AlphaGo, and if you read it, you would understand that the previous techniques used for chess just don't work for Go, just too large of a search space, right? So you need to do something. So they add that intelligence to it. And the reason why reinforcement learning used for poker game, right? Again, it's very good for poker because it's a game, it learns from playing with others, right? That's a very effective strategy rather than trying all random, possibilities. Sorry for a long answer, but there's no simple answer to your question. Like if you want to know whether there's anything we can find or there is an easy medium we can build on so things will be better generalized, I don't think it's that easy, like even for a sub problem like RL.
Yeah, I understand. Like you were actually in short saying that the simulator destroys the capability of generalizing easily, right?
Yeah, simulator alone in just RL, not talking about all the other interesting stuff in AI beyond machine learning, right? It just kills it alone because it's any general code and it's not a hypothesis. We've seen simulators that are completely different, right?
I understand.
So the way NVIDIA tried to solve it is just try people to use certain type of simulation using CUDA and using their libraries, but that's not a solution, let's be honest, right? This is just their way to keep the market around their accelerators. Yeah.
Okay, I will
but
proceed
it would work
with
for certain domains. Like we had to accelerate, like if we want to run those workloads efficiently right now, we also do what NVIDIA does, right? We also try to map them as much as we can on an accelerator, right? But people will come up with other creative ideas, right?
Yeah, thanks a lot. I will move to the second one.
Yes.
So the second one is a bit different. It's closely related to computer architecture, actually.
Yeah.
So we have seen in several conferences works, mostly I think theoretical, and some of them are practical, on boosting several microarchitectural components, such as load value predictors, prefetchers, like the work that we've done with Rahul. Memory controller, self-optimizing memory controllers, like the paper from Safari also. And people are proposing more and more of these, right? And they're trying to make them more fancy and more fancy and more fancy, and they will probably do it. So there is a barrier that when they go more fancy than what the technology enables, they need to publish theoretical work, right? So their design is not feasible. So they just need to give some proof of concept results on what will happen maybe in 20 years if someone tries to put an LSTM in a prefetcher, let's say. So the question is the following: would it make sense to try and do this study of, characterizing, understanding, quantifying the feasibility of different ML models applied in different levels of the microarchitecture? There is a different latency, memory size trade-off when you apply it in a load value predictor. There is a different latency area overhead when you apply it in a memory controller, a different one when you apply it in the prefetcher. And there are several components where you can plug this in, right? From security, the different domains also, security, like the work from Perspectron from Daniel Jimenez, to performance, to QoS, like you could do RL for bandwidth partitioning in caches. There are many things you can do. And the question is, would quantifying the feasibility of these models make sense? And the biggest question is, does it make sense to study theoretically these problems? Like, let's go, like, we want to be more fancy than what's possible in our technology right now. And we're going to throw a deep RL model in our prefetcher. Does this make sense as a study, or we should be like, okay, technology enables us 32 kilobytes in the prefetcher. We will stick with these and see what the best we can get out of the models. That's a hard question, I guess, still, but yeah.
I think here, whether it's worth, I think academia at least should do this type of research, for sure. That's my opinion. Probably if it would be an industry, that would be too high of a risk, right? There's not immediate return. If I put my academic hat, I would say, yes, it's worth it, but I would still be very careful in selecting those problems. So essentially, you go into this risk territory where you can explore things that never will be feasible, right? So you might like it. It depends on what style of research you like, whether you want your things being deployed relatively soon versus 1, 3, 5 years from now versus never potentially, right? But if you find something that others overlooked, right, then you might have a very high reward, right? People already definitely doing it. People apply ML techniques in Google for chip design. People apply ML techniques, including RL, for chip design. They are all looking to analyze. I think you've probably seen from Partha's group, right? The analysis on prefetching in the cloud,
Yeah.
right? So those techniques do work. Finding there's a nice domain that it actually do work. You need to be reasonable. Like, people use machine learning for, say, branch predictor, like long time ago, before even ML being popular, right? They just did a feasibility study, how far we can go with prediction, right? And at some point, you just need to make a decision for yourself whether you're excited about it, right? So you can, whether you like to keep working on the branch prediction, it's important for you personally, like intellectually, because there is still a value, but then there is a risk versus the potential reward. So this is the equation you kind of need to decide for yourself. How much room do you have there versus, like, for example, if you think about, oh, what I want to do, as you said, RL for IO traffic. So you might make an estimate on how fast the RL would ever work. And you can speculate 10x faster, 100x faster than right now. And even if that is not feasible, so then you make a decision, this is probably something like 5-10 years from now, in the best case, right? The trick is to find that. The really tricky and interesting thing is to find something that's new but somewhat feasible, even with some assumptions. So trying to make as minimum assumptions as possible, right? So that would have a more immediate effect and still be novel enough. It's a tricky thing, right? You are playing this game on what's feasible versus not. Like, for example, in my group, I usually try to force the student to do everything on a real system until it's just impossible to do it. Like, we only go for simulation where there's no other way, right? Because I found that by starting with a simulator and doing research in a simulator, we can easily bypass on a lot of interesting problems, right? So I always force students to get all the motivational results, at least on a real system, right? Show me the evidence and prototype some initial ideas on a real system. That would make things had an impact within me. If the idea is good, within 35 years, say, if your ideas are good, right? It doesn't mean but that's the style of research you want to do, right? This is not like about fundamentals. Some people would work things on circuits, and then you would always start with a simulator. There's no other way, right? Yeah.
Okay. Thank you.
In this domain, for example, like even if you take ML, there are people who start experimenting with new ideas on speed up ML workloads, starting with a simulator already, running, say, on something like GPU-C in some of these kernels. I do work differently. I think you only jump to the simulator last minute where you're confident the problem exists, right? And then you model it. And then maybe after that, if it's critical, like for example, we work on multi-tenancy, and the multi-tenancy is not supported properly in GPU right now. At the end, the solution needs to be evaluated in the simulator. But all the evidence that the problem exists and that existing solution is not adequate, we collect on the real hardware, on real NVIDIA GPUs. the problem, like the minute you go for simulators, all your workloads are very limited, everything very limited, so you missed one real picture, right? Yeah. But again, remember, this is a very opinion-based thing. So it's like a lot of things I said here is based on my personal opinion, right, and experience, rather than just raw facts that other people have different opinions on how that can be done.
Yeah, the question is also opinion driven. Like I want an opinion. It's not about. So there's no definitive answer. I'm just sometimes, you know, it's like I feel that there should be a general methodology or a barrier towards understanding what is feasible and what is not, so that because some things might not make sense even in 10 years from now. That's what I mean. In
my work, especially during my PhD thing, I do a lot of work in architecture itself, right? And I always try to, my always goal was when I try to design something, I try to design things simple. So why is it? It sounds like, what's the big deal about that? Well, it's very easy to come up with a design that's overly complicated and looks fancy, but that's not going to make, you know, happen. Like people, especially if they want to develop something that will be used in practice, the simplicity is an overestimated metric that's hard to measure, right? So coming up with something that maybe not giving you the best performance, or let's say when I work on compression, not the best compression ratio, but something that's actually feasible, it has a contribution on its own, right? Look, I never come up with an algorithm that's better than the standard algorithm, but I come up with something that's very, very simple that might be feasible now. So I feel I kind of solved the feasibility gap. I found that's very exciting in architecture, trying to come up with something that's elegant and simple, even sacrificing some performance bits for that. Yeah. But I personally think it's a style of work. Some people like to build, you know, interesting and fancy designs.
Mm-hmm.
I mean, the beauty of academia, you decide what you want to do, and no one forced you, right? You have the freedom to decide what you like.
Yeah, that's true. Yes. Yeah. Thanks a lot for answering.
Yeah. Okay. Any other questions?
So I also have a couple of questions, like one more practical one and another one maybe more like maybe to buy some of your perspective. So the first one, it's about like this last work you presented is the first time you use TensorFlow as well as a backend.
Mm-hmm.
So does it mean that you found a way of building tools that it generalizes across different backends, or it is like also like a lot of like extra work that had to go in there in order to like support the two backends, and you had to do this in order to like show like the potential of what you could do with your tool?
Yeah, so there are, where possible, we try to make things generically, right? It works across frameworks. In some cases, it's just impossible. So it would require some engineering. I don't think anything I talked today wouldn't be possible to do with TensorFlow. It's just TensorFlow is way less friendly to low-level programmers in general. That's the honest answer. So it's harder to develop on top of it. So I usually tell Google people what's good, that we believe is good, and then they can implement it themselves. When there is a chance to build something that works on both frameworks, we always do it, right?
Mm-hmm.
I think my honest opinion right now, TensorFlow is losing the battle to PyTorch overall. 3 years ago, PyTorch was dominant, PyTorch was emerging. TensorFlow was dominant, PyTorch was emerging. Like this year, we did an experiment for a few months. I think I mentioned that number, 88% of the GPU hours spent in the vector cluster PyTorch-based, only around 9% TensorFlow-based.
Yeah.
And the same thing in the industry.
I was surprised because like you also showed today results where like TensorFlow is significantly more performant, right? Thanks to this kind of graph execution mode.
There is one thing you would have to learn on the real life dealing with ML researchers. The performance is not a big deal for them, unfortunately. So, for example, I'll give you one anecdote. In Vector Institute, like everyone cares about in architecture community about tensor cores. You know how many people use tensor cores at Vector Institute? There was one experiment of the whole year running tensor cores. All other experiments were not using mixed precision at all. Why? Because they've heard before that it might affect convergence. You need to do extra steps to make sure that the models don't diverge. They won't bother. They had a lot of other problems to solve. So we might come up with a lot of fancy stuff, but no one will use them. And my students gave tutorials explaining how to use, you know, tensor cores and they don't use it. And yes, compute is underutilized, but it is what it is, right? So I think NVIDIA realized that. They remarketed their mixed precision into TF32, come up with a new precision and make it automatic. So that's the only way for things being used. So people won't use things otherwise. So that's part of the problem, is a lot of those things. So when you tell them that, say, TensorFlow would run something on a RHEL twice faster, that's not a deal breaker for them. They need to make things 100x faster. So this 2x is not a big deal. Like PyTorch convenience to run experiments is a bigger feature than any extra speed than TensorFlow does right now.
Yeah, makes sense what you say, but it was surprising, like to think it like that. Yeah.
Surprising, and it was surprising for my students when we did all the studies with ML researchers, but that's a reality. So you had to do the reason why would PyTorch ever, like right now I show you 2x gap, right? You know what, when we started like 3-4 years ago, PyTorch was 10x below TensorFlow, and it was still very popular. And that popularity and simplicity outweighed performance. And as people spend more time on PyTorch, people pick up it, like Facebook pick up PyTorch, and they keep fixing it. So in a lot of workloads, you won't see a difference anymore. But they had a huge gap right now, but some people excited about PyTorch, so that performance was added when it was needed.
Yeah, makes sense.
So the programmability and the ease of programming is usually underestimated in academia, in my opinion, and especially in architecture papers. Like everything is about performance, fault tolerance, power, now carbon footprint. But the ease of programming is such a difficult metric to measure. Like lines of code doesn't really reflect it, and but it's so important in practice. So that's what happens, right?
But like TensorFlow now also moved into this kind of like hybrid way, of getting the best of both worlds.
They moved TensorFlow 2.0 there, but nobody cares. It's too late.
Yeah.
Like remember, Intel was also coming to the mobile market eventually, but it was too late. Like, you need to get it the right time. When the Apple asked them to do it, they should have done it then, not afterwards, right? Now it's hard, right? So essentially right now they lost that. They had the chance when they were in parallel with MX to go into that route, and they were too slow with it. And they're making this decision with a very, largely, in my opinion, for example, again, this is my biased opinion, but I think they should realize that they should support PyTorch much earlier. First, they claimed, as far as I remember, that TPUs will always be supported on TensorFlow. Now, look, PyTorch plus XLA is now all supported on, and runs on GPUs, right? Like the whole pipeline is there because that's what people using, right? But you should have done it much earlier, right? In my opinion.
I see.
I think right now the main use case I see for TensorFlow is an industry, and especially when people have some dependency in their workflow, like deployment and all of that, where TensorFlow Lite is used and things like that. But for researchers that just train the model to make a concept or publish a paper, none of that features of TensorFlow has a big value.
Yeah, I agree. Then my second question, it is more like taking a step back and thinking about everything that we are now considering. It's about having this kind of execution model, where you have this host accelerator as basis. So CUDA, OpenCL kind of languages that they are actually propagating that, all the way to the execution. My question is do you think that there is any important fundamental limitation that it is propagated from this kind of unquestioned decision nowadays? And if so, would it make sense to have an alternative execution model to accelerate machine learning in data centers? Or this is just working good enough? Yeah.
Great question. I don't have an answer, otherwise we would work on that already. I think it does definitely have a value. The main problem is the reason why it works that way is that existing ML still had tons of code that has to work on general purpose hardware, right? So yes, GPU can run anything, but how well is going to run regular, control flow heavy code, right? That's a problem. So you still had to run certain things in a different way, whether you can completely dispatch and disconnect things. That would be interesting. I would love to see the works that wouldn't just follow that master-slave relationship between a CPU and accelerator. They all follow in that principle. It's definitely seeing something that with accelerator would be an independent and because they're Turing complete, they can run anything, but I mean, the performance on a random code is terrible. Like you can run everything on CUDA, right? But the problem is
it is. Yeah. It accelerates what it accelerates. Otherwise,
it does certain things well. Like that's based on the the courses that we're all teaching, I guess, with me and Honor. Like I mean, there's only certain things that it does well because it has a good trade-off, but not everything.
Yeah.
And the workload we write has a lot of other things beyond the hot kernels.
But this also, I was thinking, like this question is triggered also by like the interface you have, like this kind of kernel granularity, where you are always sending kernels like at a very small granularity, but actually we are trying to compensate for that by just like having a lot of data to process, right?
You're absolutely correct. It's a common problem that this kernel interface, when the low kernels had poor utilization, and we had to come up with creative ways to deal with that. It's a problem right now. Accelerators only work well when they get big pieces of work to do, right? If it's not, then everything breaks and it's very inefficient.
But it's not going to break, no? Like if you see ahead in the future, like it's going well. It's not ideal, but for what it is used, it is good enough. Or that's a bit my question, like, or there is a moment where like something is going to break or not
feasibility analysis, how much better you can do. So right now, say if you take DNN workload, that it's very heavy on matrix multiplication, that's not too bad because most of that overhead can be hidden. But I'm just saying that I don't believe the whole future would be just with deep learning alone. And like a RAL is one demonstration where this whole thing is not great, right? We keep jumping. Like one of the optimizations we were doing, we were like avoiding all this traffic back and forth, right? We were grouping things, just that the code becomes more and more complicated and it becomes hard to manage, and the tools are critical to do it. And I hope things like more interesting algorithm will appear that would trigger people to be more creative as well, right? But I agree with you, like right now, the existing interface is, first of all, it's boring and it doesn't look amazing, but it is what it is right now, right? I don't see an easy way to get rid of it.
Yeah, and it's simple, as you said before, right? And if as long as it's simple and works well enough, then yeah, it is.
People have to have another killer use case, but it just doesn't work, and there's alternative, right? So people then would switch.
I completely agree. Thank you for the answer.
Yeah, thank you.
Thanks, David.
Okay, I think we are well over 2 hours right now. So if there are no more questions, should we stop here or there's more questions?
I can ask one small question, but then you can just maybe keep it small also.
Yep.
So the question is that I would kind of extend what Konstantinos was mentioning. So basically, we in our lab we are also kind of looking at this problem, that how we can use ML or other RL techniques in the microarchitectural predictors, right? So the key limitation that we find normally is that we don't have a hybrid simulator at all. Like as a tool, we don't have the hybrid simulator. So if I go back to the definition that you mentioned, I think you mentioned somewhere in slide 84 or something, that we have the simulator there, which is simulating the environment for the RL agent, right? But in this case, the simulator would simulate the core, basically, like processor core, right? So then the problem stays the same, that you are like going back and forth from one domain to the other domain, and then so essentially you have a fully like out of order core which is implemented in some part of the CPU, right? And then you have let's say if you're making your predictor as a deep RL system, so let's say which is managing the memory scheduling, right? But that's executing in GPU or maybe something else. So my question is like, is there a tool or can we envision a tool that simulates a core? Like it's in the end, at the end of the day, it's still a microarchitectural simulator, right? But then all the predictor engines that we have in the microarchitectural simulator is kind of modular enough to be replaced by intelligent agents, let's say, which is written in Python, or which is using, let's say, deep RL or maybe supervised learning for that matter.
I think that's doable. It would require some engineering. I wish industry would be cooperative with helping to build those simulators. I think there's there's a essentially there are two problems here. There are simulators itself, and I guess there are things like Gem5 that is very cycle accurate, and they model every little step, but had a humongous overhead. And there are things like Livian's Accords group, right, in Europe works, right? That's I think I forgot that Sniper or something. I don't remember the exact name. Yeah. So they had a different, concept, and that can be fundamentally different and change the game and how fast the simulation would work. I really like this line of work. I think we can solve the problem of components being modular, like you described, like you can write them in Python, and then we would compile and inject the code of that Python into the simulator itself, so it's compiled, so you don't need to go jump. I think that problem can be solved, right, with the clever engineering. So you can describe the component and flexibility of what you want to try out in a high-level language, right? But to avoid the frequent transitions back and forth, you would take the Python code and efficiently compile it and inject code gen into the simulator itself, whatever simulator.
But I think, I mean, we can still write something on the bare bones C++ API. And for that matter, we don't have to write in Python. But the problem that I have in mind is that in the end, this intelligent predictors would, we expect it to run on GPU, where we can do like deep computations, right? Yeah. But then you have to turn back those predictions or the actions that you want to take to the actual core model. The core model would give you the next state for you, right?
Okay, let me be honest. I think that predictions won't be a bottleneck when you deal with CPU simulator. I think that the simulator itself will be so slow that predictors, you can use CPU, not GPU.
That's true.
So I think that the simulator, especially cycle accurate, is so slow, so none of that would matter as much. And you can use for inference. Like you probably heard that Facebook until recently used for inference frequently use CPUs, right? Because they're not as bad, right?
Yeah.
For inference. Not for training, but for inference, it might be good enough. So for you, for sampling the environment, it might be good enough, right?
I see.
Yeah.
Okay. Yeah. Thanks.
Okay.
I think that answers my question. Anyone else?
Yeah, I think we're already out of time. I mean, I may have some questions, but and definitely comments also. But I think this is very interesting work, Gennady, for sure. I especially like the reinforcement learning part, since that's. I agree with you that at least in the current state, the deep neural networks cannot be the answer. Cannot be the only answer. Let's say.
It can be the only answer.
Yeah, for learning in general, right? And I think reinforcement learning certainly has a lot of benefits in terms of being unsupervised and interacting with the environment, and basically improving over time. And we're actually using reinforcement learning in our research also, as Rahul and Konstantinos mentioned, to improve microarchitectural components. So it'd be great to see more work in this area for sure. I'm assuming you're doing more work in this area that are not published yet, but.
Yep. Yeah. It's
I mean,
interesting and promising. I agree.
Yeah, certainly, and I mean, I don't have any question that I don't want to keep you longer. Also,
we can always sync up with you and talk more.
Exactly. Yeah, we can sync up maybe in person, privately, separately. But thanks for presenting your work again, and. We'd be happy to welcome you again whenever you want to present.
Yeah. Thanks a lot for giving me an opportunity to finally present this long talk about how the tools were built, right?
Sure. Yeah, and you have a lot more work, I know, to present. So I'm sure you can find some other stuff that is also quite exciting.
Yes, we still do systems and computer architecture work. It's just that 2 talks were focusing about ML. There is other things we do.
Exactly. Yeah. Exactly. Okay, well, unless some other people have questions, I think we should probably conclude. Yep. Maybe if someone has a burning question, they can ask.
Yeah, and if you have burning questions, it's okay. You can always reach out to me later on or email. I'm happy to answer questions about the work and can connect you with the students who actually did all this work for a very low-level question, implementational questions, if I can't answer myself. Yeah. Okay.
Okay, sounds great.
Yes.
Thanks,
Thank
Kenna.
you. Yeah, bye. Have a nice
Take
evening.
care. Bye-bye.
Bye.